Swayam Prabha. Digital India. Educated India.
Hello friends, welcome back to the lecture series of BSc with Chemistry, Physical Chemistry Paper 4. This is lecture 5 of module 2. Now friends, from this lecture we will see the different types of reversible electrodes. Basically, the electrodes used in the reversible cell, they are called as the reversible electrodes. Now various types of electrodes are discussed in this lecture. Let us first discuss this metal ion electrode. Now, what is called as metal ion electrode? As its name indicates, when a metal is dipped in its ionic solution, it is called as metal ion electrode. Say, for example, if I take a zinc rod and uh, if I dipped it into zinc sulfate solution, or a copper rod into copper sulfate solution, so it forms the metal ion half cell. Basically, we have seen the Daniell cell earlier. Now it comprises of the zinc rod in zinc sulfate solution and copper rod in copper sulfate solution, and both of these half cells are connected through salt bridge, and then it is a complete cell. Basically, in this particular reversible electrodes, each of these electrodes are representing the half cell, and we are discussing these individual half cells throughout this discussion of reversible electrodes. Now herein, as I said, if I take zinc dipped in zinc sulfate solution or copper dipped in copper sulfate solution, so whatever cell I am taking, it depends on you whether you want to act it as anode, or you want to act it as cathode, or you want to act it as negative electrode, or you want to act it as positive electrode. Wherever you want, you can connect it. Basically, depending on this electrochemical reaction or half cell where you connect it, the overall cell representation will change. Anyway, we will discuss the EMF of this cell or this half cell in these types of electrodes basically. So now, whatever electrode you take, like zinc dipped in zinc sulfate or copper dipped in copper sulfate, the cell reaction will be, if it is we want it to act as anode, it will be giving like this metal is giving into uh, n number of electrons, and metal becomes this number of oxidation state will become positive. So now, this is in this direction, from left to right it is oxidation, and from right to left it is reduction. So depending on whether you want to represent where you want to represent it, this sign of this particular reaction will change. If oxidation, it will go from left to right. If for reduction, it will go from right to left. Okay, so now depending on this, the Nernst equation of this type of cell is given by E cell is equal to EMF of standard cell minus 2.303 RT upon NF log of m to the power n plus, that is the oxidation state of the metal. Now if E is the oxidation potential, my Nernst equation becomes like this, and if E is the reduction potential, say at 25 degrees centigrade, so this particular EMF of the cell is given by this particular expression. So now this particular equation, basically this particular equation, this shows that the potential depends on the concentration of metal ions. Okay, and we can also predict that if the electrode act as negative electrode, the equilibrium shift towards right. Okay, and more ions are produced basically. Okay, if I connect, say if this metal would have been zinc, so if I connect in Daniell cell the zinc electrode, so the equilibrium will shift towards the right hand side electrode. Okay, and more ions of zinc will produce. And if this electrode acts as positive electrode, then the equilibrium shift towards left side, and more ions gets deposited, leading to decrease in metal ion concentration. Say for example, if this metal ion electrode is copper electrode dipped in copper sulfate solution, and if I connect it to Daniell cell, so it will be a right hand side electrode, and therefore uh, the this becomes the positive electrode, and the equilibrium will shift towards the left hand side, and more copper will be depositing, leading to decrease in metal ion concentration. This is what is the meaning of this metal ion electrode, isn't it? Now secondly, the amalgam electrode. In this type of electrode, see, metals like sodium, lead, etc., they react with water, and hence they cannot be directly used as electrode. So the amalgam is dilute solution of metal in mercury, correct? We call it as amalgam. So amalgam essentially behaves as a pure metal, except that the activity is reduced due to dilution. If I take the example of this lead mercury and lead ions, so the net reaction will be this. If I connect it towards anode side, it will be from left to right. So this amalgam is giving you lead ions plus 2 electrons. This is oxidation. You can see in half cell reaction, you can write it down on left hand side. Or if you write down lead plus 2 electron giving you lead mercury amalgam, so you can write it on right hand side, and reaction will go from right to left. So the electrode potential in this case will be given by this particular cell reaction at 25 degrees centigrade. Okay, so this is another form of writing the reaction. In this case, RT upon 2F. If I substitute RT upon F value, so it gives me 0.0591. Okay, now here lead, the concentration of lead is the, basically this is the concentration of amalgam, and it may not be equivalent to unity. That one has to keep in mind. So this is the electrode which is amalgam electrode. We can utilize this concept in many of the half cell reaction. This is another basic electrode, the gas electrode, which I guess we have also seen earlier, this particular type of electrode. So if I consist or this particular gas electrode, it basically consists of the pure and dry gas which is bubbled through the solution of its own ion. Now you can insert any metal like platinum wire. Says you can take platinum wire which is attached to platinum foil. It is used for the electrical contact, and you can dip it into the solution of hydrogen ion, isn't it? Usually what is platinum electrode? So if I take platinum wire and below there is platinum foil, and the whole assembly is encapsulated into a glass electrode, and if I dip this glass container containing platinum and platinum foil in the solution containing hydrogen ion, and inside this glass tube if there is a hydrogen gas, so I can represent the half cell like platinum, this is H2 gas at given pressure, and which is in contact with the hydrogen ion. So I can represent this half cell reaction like this. Okay, now once again, if this is if I want to act it as anode, this particular reaction will be represented like half of H2 is giving H plus 2 electron, or H2 giving twice H plus 2 electron also I can write down in this case. So that means the reaction will go from left to right. So this if I connect it on the left hand side electrode, or if I connect it on the right hand side electrode, again I can write down the reverse reaction, that is the H plus electron will give you half H2. In this case, the cell EMF is given by this E is equal to E standard minus 2.303 RT upon NF log of H plus upon this pressure of H2, square root of pressure of H2. So now the standard EMF of hydrogen electrode is taken as 0. This we know, isn't it? So if pressure of hydrogen gas is maintained at 1 atmospheric pressure, so my equation becomes this. So this quantity is 0, and I can now write down like this: E is equal to minus 2.303 RT upon F log of H plus ion concentration, and this is nothing but at 25 degrees centigrade, this E is equal to minus 0.0591 log of H plus ion concentration. This is nothing but your pH. So I can determine my pH using this particular electrode. Okay, but you can also say that some other electrode reaction involve a gaseous species such as oxygen or chlorine. Such reactions must also be carried out on the surface of an electrochemically inert conductor, say in this case like platinum. Okay, so this gas electrode also is very important, and we can see many numerical based on this particular concept. Say the concentration is given, EMF, standard EMF is given, and I can find out the EMF of the cell using the HIN concentration if HIN concentration is given. So this is particularly simple. So electrochemistry gives you a lot of aspect to carry out these small phenomena. We will see some of the numericals based on this concept as well. Let us move ahead. Yes, this is another important concept. Now, metal insoluble salt electrode. Now, in this case, this type of particularly electrode, if I see, they consist of metal rod which is in contact with insoluble salt of metal and a second solution containing anion of the salt. You can see here, containing anion of the salt, isn't it? So this example has been taken. So what is my metal is silver. What is insoluble salt of metal is silver chloride. And what is the solution containing common anion is KCl solution, which is saturated. So silver electrode is dipped in the silver chloride solution, and the silver electrode in presence of silver chloride, and it is in presence of saturated KCl solution, isn't it? So my electrode reaction, it goes like this silver ions goes into solution and reacts with chlorine, they forming this solid silver chloride. So my electrode reaction will be like, if it is anode, look at it, oxidation, Ag plus Cl minus is giving you AgCl. Okay, and if it would have been acted as cathode, the exactly reverse reaction I would have written. So the overall reaction can be written down as Ag plus Cl minus giving you AgCl plus electron. You can see the release of electron. You can see the release of electron. So electrode reaction, and this is particularly the cell reaction. So the overall reaction of the cell is this. So you can see this release of electron. So the electrochemical potential will be given by this particular equation, E is equal to E standard minus 2.303 RT upon F log of 1 upon concentration of Cl minus. At 25 degrees centigrade, I can write down the overall reaction by considering 2.303 RT upon F is equivalent to 0.0591. So I can write down this particular type of equation. Basically, the electrode reaction involves only the concentration of chlorine ion, and the electrode in this case is also said to be reversible with respect to chlorine, isn't it? So this particular reaction shows how an electron can be released or taken up in such an electrode or at such an electrode, and therefore it should be noted here that the potential of this electrode depends on the concentration of the anion in the solution. It does not depend on the concentration of metal ion. This is important to see. You can see over here, it does not depend on the concentration of metal ion, and that is why it differs from metal ion electrode. I can take another example of this type. So the another example of metal insoluble salt electrode is the mercury sulfate electrode, that is Hg2SO4 in contact with SO4 2 plus electrode, isn't it? So I have shown you this is the particular electrode which I have discussed over here. This is silver chloride electrode here. Now I can also see the another electrode which is I can say the mercury sulfate electrode, that is Hg2SO4 in contact with SO4 2 plus. Uh, this particular type of electrode, these electrodes are used in standard Western cells. You can recall from the 12th standard electrochemistry. Now the metal insoluble salt electrode, usually they consist of a metal electrode in contact with the in contact with an insoluble salt of the metal, isn't it? That is what we have seen. Now you can say it is partially coated with the thin layer of an insoluble salt of metal. Now this congregation is then held, that is metal, that is covered with the partial coverage with the thin layer of insoluble salt of metal. This congregation is then can be held in contact with the solution containing the anion of the insoluble salt, say silver chloride hai to in case of that it is in silver chloride. Now, electron transfer basically occurs between the metal atoms of the electrode and the metal ions in the insoluble salt. Correct? You can see over here, isn't it? So, these electrodes are basically constructed for any metal with its insoluble salt dipped in a solution containing the common anion of the salt and not the common cation. And therefore, there is no question of having metal ion kind of thing. So obviously, in this case, the anion in the solution should come from the highly soluble electrolyte like KCl. And the most frequently used electrode of this type is the, we can say, calomel electrode. You can see over here. Now, this calomel electrode, we will see further also the construction, the detailed construction of calomel electrode. But for now, this calomel electrode is consist of the mercury in contact with the mercurous chloride. You can see, isn't it? So here there is mercury in contact with mercurous chloride, and this is particularly known as calomel as a paste. And over this particular calomel as a paste, uh, we put this solution containing chloride ions, say KCl, usually saturated KCl we put. So the electrode which is represented as, say, you can say Hg2Cl2 in presence with chloride ions is, it is known as saturated calomel electrode. Now, if you vary the concentration of KCl, it varies. Like instead of saturated calomel solution, then we can say standard calomel electrode, and there are other variations we will see later on also. Now, this particular electrode is usually made with the zero point 0.1 molal or saturated KCl solution, and depends on that we can name it. Basically, the paste of mercury and calomel is made for this electrode by mm, thorough grinding, and that grinding it requires in laboratory say 2 to 3 days, and this particular grinding is then washed several times with the small portions of KCl solutions, very minute fractions, and this paste is placed in the clean electrode vessel in which some amount of pure mercury is also trapped at the bottom, which has already been placed, and then you can fill up the paste, and the rest of the vessel is then filled with the KCl solution, say saturated KCl solution in case of saturated calomel electrode. Now, this tube at the end of which a piece of platinum wire is sealed and placed in the vessel is basically uh, shown over here, which something looks like this in the laboratory. So this is the porous, this is a capillary where you can keep, your calomel paste over mercury and then KCl solution. Okay, and then porous fitting also you can substitute, basically that can be sealed with the help of agar agar gel or something like that. Now, some mercury is already placed inside this tube before filling the calomel paste, that one has to keep in mind. And this particular half cell electrode can be utilized for many reactions, or many laboratory studies. We can use this calomel electrode, isn't it? So this is how this very important metal insoluble salt electrode is constructed. We will see the construction of calomel electrode further in this lecture also. Now, redox electrode. In case of redox electrode, or which we also call it as oxidation reduction electrode, as its name indicates, in this type of electrode, say you can take the example of ferrospheric, cerospheric. All these are the example of redox electrode. In this type of electrode, the metal like platinum rod is dipped in the solution which is containing the ion of species in two different oxidation state, like ferrospheric Fe2 plus Fe3 plus. So the redox couple of same species act as a source of EMF. This is very interesting. You can take any pair, any redox pair. As I said, Fe2 plus Fe3 plus serous you can take, which is the routine practice of experiment to perform in the laboratory. Now, if I consider the platinum rod, which is dipped in solution of Fe2 plus and Fe3 plus, the redox reaction will be given like, if it is at anode, Fe2 plus will give Fe3 plus plus electron, so electron will be released at anode. In case of cathode, the reverse reaction can be written, isn't it? And for any such reaction, the Nernst equation is given by this. So E is equal to E standard minus 2.303 RT upon NF into log of Fe3 plus log of concentration of Fe3 plus upon concentration of Fe2 plus. So at 25 degrees centigrade, I can write down this like this. So my EMF equation will be forming this kind of, will take the shape of this equation. Now, in this type of electrode, the potential depends on the ratio of concentration of two species. And in my experiment, I can very easily find out this ratio, and therefore I can find out very easily the EMF of the cell, isn't it? This electrode has been used very extensively while studying the redox reaction inside the laboratory. Now, we will see a very important reference electrode. Now, you can see over here, this is hydrogen electrode. Now, in this electrode, basically two electrodes constitute an electrochemical cell. This we know since long. I mean, till now we have discussed. And we know that it is not possible to determine the electrode potential of a single electrode. And these two, I mean, whenever the two electrodes as a half cell, when they combine to form a cell, then only the cell EMF can be measured experimentally. Now, whatever, I mean, however, although the two cells can be connected, if I know the cell EMF, or if I can find out the difference of these cells which are connected together, so I can find out the EMF of the cell. This is what is the principle. So basically, I cannot find the EMF of any particular cell. I can find the difference. So knowing the cell EMF from the difference between the potential of two electrode is what is the principle in this particular electrochemistry section we are discussing. Now, in order to determine the relative tendency of two electrode to undergo the reduction or oxidation, the potential of one of the electrode has to be arbitrarily fixed, and that of the other is measured with respect to the first. So one has to put one as a reference point, isn't it? So in this case, the standard hydrogen electrode is assigned with an arbitrary value of redox potential, that is 0 volt. We have discussed this during our discussion of electrochemical series, why we have placed this hydrogen electrode at this exactly at the center at 0 volt. Now, in this particular type of electrode, the hydrogen ion with unit activity, I mean unit concentration, is in contact with the hydrogen gas at 1 atmospheric pressure, and therefore its activity can be taken as unit. This particular figure I'm talking about, isn't it? So the electrode basically whose potential is exactly known are known as secondary standard or secondary reference electrode. Now, if I talk about hydrogen electrode, the electrodes consisting of glass jacket containing a glass tube, you can look at this figure. Look at this figure. So the electrode consists of a glass jacket containing glass tube, and a platinum wire is used, or basically it is fused through this glass tube, and at the bottom there is a platinum foil. So this is a platinum wire which is fused through this glass tube, and it is connected, electrically connected through to this platinum foil at the bottom of the tube. Now this attached platinum foil is coated with platinum black, and it is immersed in 1 molar hydrochloride solution. And also hydrogen gas is bubbled at 1 atmospheric pressure through the jacket, to this jacket. You can see, isn't it? So hydrogen gas at 1 atmospheric pressure, pure and dry hydrogen gas is bubbled through this particular jacket. And this is particularly the glass jacket, and this is connected, this wire is connected to this foil, platinum foil, which is coated with platinum black, and little mercury for good electrical contact is has been put over here. And this overall assembly is dipped into 1 molar HCl, and now you can bubble the pure and dry hydrogen gas through this cell. Now the potential of this electrode is dependent on the concentration of H plus ion, and if the concentration of H plus ion is maintained at 1 molar, the standard electrode potential becomes 0. Look at the Nernst equation, isn't it? So standard equation, standard EMF or standard electrode potential of this EMF will become, or this cell will become 0. So the if I look at the cell reaction, so hydrogen gas gets adsorbed at the platinum foil, and the redox reaction will be represented as half H2 will give you H plus plus electron, the oxidation reaction. And correspondingly the Nernst equation is given by this. So at 25 degrees it is represented like this. Since this is 0, the standard electrode potential, if it is 0, so it will be represented like minus 0.0591 log of H plus ion, and that is what is earlier also we have seen E is equal to 0.0591 pH. So if I know the H ion concentration of particular solution, I can find out the EMF of this cell. Now, what is the important advantage of this particular cell? The important advantage is that the standard electrode potential is 0 volt, since it is primary reference electrode, and hence if it is used as reference electrode, the EMF of the other electrode is equal to the cell EMF. So whatever electrode I connect, and if I find out the cell of that particular EMF, EMF of that particular cell, the EMF of that cell becomes the EMF of the complete cell, isn't it? So the hydrogen electrode as such becomes reference electrode, primary reference electrode. Also, there are certain disadvantages. What are the disadvantages associated with its assembly? Now, this hydrogen electrode is made up of a delicate glass assembly, and it is simply difficult to handle this glass assembly, and therefore the electrode needs apart from this dry and very delicate assembly, the electrode needs to be this electrode needs to have a very dry and 100% pure hydrogen gas, which is very difficult. Always there is slight contamination in gas, and this contamination usually leads to abnormal results. Now the pressure of gas bubbles or whatever the gas bubbles through this particular glass assembly, it should be exactly 1 atmosphere, and that is also another difficult task to maintain. That should be that it should be maintained at exactly at 1 atmosphere. So it becomes difficult to number one, handle such a delicate assembly, number two, to get dry and pure 100% pure hydrogen gas, and number three, very difficult to maintain 1 atmospheric pressure. And therefore due to this reason, it is not that way a popular reference electrode. Okay, so this is what is all about the hydrogen reference electrode. So friends, we will stop here in this lecture. We will see in our further lecture the construction of calomel electrode and its use, and the concentration cells. and then corresponding numericals also we will discuss during our further lectures. Thank you.